Hello everybody, we're Team Raptor and this is our final project presentation. My name is Alex and I'm joined by my teammates Isaiah, Zachary, Kelvin, and Richard. As an overview, we're going to talk about what our project is and its requirements and how I broke up the responsibilities within the teams. And then we're going to go over a full overview of our UAV and UGV systems and our results, and then we're going to give you a conclusion. For our project, we had to design a UAV and UGV subsystem to complete the following challenges. Challenge 1 was just the UAV. The UAV had to autonomously scout a football field within a 30 by 30 yard section to find a random Aruka marker that was deemed as the correct Aruka marker. The requirements here was that it had to be able to start from a random starting location and land at a random landing zone that would determine the day of the competition, and then it had to be able to correctly identify the correct Aruka marker out of the 5 total Aruka markers that were placed on the field, and with a time all under a time limit of 10 minutes. Challenge 2 was the same thing for the Scout UAV, except there was no time limit, but after the Scout UAV found the marker, it would then have to relay that marker's location to the ground vehicle, and the ground vehicle would then deliver a payload. One additional requirement that was added here was the use of peer-to-peer communication between the UAV and UGV. This meant that the UAV and UGV had to communicate directly to each other and not through a host. Lastly, there was a bonus challenge, which was to repeat challenge 2, but for the ground vehicle to deliver a heavier payload. In the top right, you could see the payload that we used, or the payload that was specified, and the Aruka marker specifications, and an example of what a field zone looked like. Here's a breakdown of all the people in the team and their responsibilities. There were 3 total sub-teams that made up the UTA team. There was the EE team, which is my team, and then the CSE team, MAE team, and then we had our sponsors.
To give a little background to our project, we wanted to highlight previous year's drone competitions and note some similarities and some differences between them. First up is the 2022 Raytheon drone competition. Pictured here is the UAV that they created for that year's competition. A similarity between this current year and the 2022 year's competition is that the UAV had to scout for the position of an Aruka marker on the football field. This is actually a similarity that our project has with each of the previous year's competition, but some of the differences are that in 2022, they only needed an aerial vehicle, whereas in this year, we are required to have a ground vehicle. Additionally, the position of the Aruka marker must be communicated to our ground vehicle this current year, whereas in the 2022 year, the position of the marker didn't need to be communicated anything. The drone just needed to go and land on the marker. Pictured here are the ground vehicle and the aerial vehicle that were created for the 2024 competition. Once again, the aerial vehicle in the 2024 competition had to scout for the position of the Aruka marker, and also an aerial vehicle and a ground vehicle were required for this competition, similar to how that is required for our competition. But once again, the position of the Aruka marker did not need to be communicated anything. The aerial vehicle just needed to go and drop some water on the Aruka marker.
Now we will break down the block diagrams for each vehicle. On the left is our UGV block diagram. Anything inside the dotted lines labeled UGV are components that are on board the vehicle. Looking in the first red box is the ground vehicle's drive system. This essentially goes from battery to motors, and it's what's responsible for providing the drive for the system to actually move. In the second red box, these are our 2 onboard computers. We'll talk more on them later, but essentially the Pixhawk is our navigation/flight controller, and it does the autonomous decision making, and the Raspberry Pi does its own processing running our scripts and gives the Pixhawk instructions. In the next red boxes are all the components and sensors connected to both computers. Outside of this, we have our ground control station and our UAV. You can see how it's configured and how it interfaces with the system. Here is the UAV block diagram. Everything within the dotted lines labeled UAV are the components that are on board the UAV. Again, in the first red box, this is the drive system for the UAV. This goes from the battery to the motors. And in the second red box is the same setup with 2 computers, except this time, instead of the Pixhawk flight controller, we have the Cube Orange flight controller. And in the third red box is all the sensors and components connected to both computers. And again, outside of that is outside of the UAV dotted lines are the ground control station and the ground vehicle and how they are interfaced with the UAV. And if you look to the right, you can see pictures of the UAV built out. I will now pass it off to Isaiah and Kelvin to talk about some of the main UGV components we used. In the interest of time, we will not be specifically going over the UAV components, as the UGV was the main focus for the EE team. However, it should be noted that a lot of the components used on the UGV were also used in the UAV.
For our flight controller, we chose the Pixhawk 6X. Its main purpose is to serve as the central processor for the autonomous missions. This choice met all of our project requirements because it had advanced autonomous operations and triple redundant IMUs, which allowed for improved reliability and fault tolerance. And it also has the necessary ports we need, which are the PWMs for the servos and actuators, the CAN port for the GPS, the I2C port, and all the Slim ports for our Raspberry Pi and for our telemetry radio. The companion computer that we chose is the Raspberry Pi 4B. What we used it for was to write all of our scripts on so it could send them over to the Pixhawk 6X, our flight controller. The requirements met by this is that it was easily able to interface with the Pixhawk over the Talim ports, and it was also able to do peer-to-peer Wi-Fi connection through ad hoc or a hotspot. The power module / distribution board that we use is the PM03D power module. The purpose of this power module was to supply power to the ESC, the Raspberry Pi, and the Pixhawk 6X flight controller. The requirements met by this power module were that it can provide adequate power to every one of our components, as well as handle a 60 amp continuous current. And from our testing, we found out we only needed a max of 50, so this fit into that category. And it also had digital power monitoring, so we could see what the current and power is through our mission planner. For our portable router, we used the Nighthawk M1 4G LTE mobile router. The reason we chose this is because I had one on standby, we tested it out, and it worked fine. The point of having this is one of the requirements for the competition is that we need peer-to-peer communication between the UAV and the UGV. At first, we tried to use ad hoc communication, which is a Wi-Fi like communication, but we couldn't connect our laptops to the Raspberry Pis through this connection. Only the Pis could connect to each other, so we had to find a different option, which was this portable router. The requirements met by this is that it assigns IP addresses to our Raspberry Pis, and it provides Wi-Fi to us whenever we need to test, and it's able to be used on our laptops and our Raspberry Pis. And it has its own battery, so it doesn't draw any power from the central power system.
The component selected for our GPS is the HERE-4. Its main purpose is to enable waypoint missions so that the drone can autonomously navigate to where it needs to go. In addition, it provides important telemetry data such as direction, velocity, altitude, and a few more sensors. The requirements it meets is that it is accurate down to the centimeter, and it is drone CAN compatible, so it integrates well with our flight controller. In addition, it provides RTK capability so that the precision and accuracy can be improved. More on that later. For our telemetry radio, the component we selected was the RFD900X telemetry modem. The purpose of this device is to facilitate connection between the UGV, the UAV, and the ground control station. The requirements that it meets is that it is robust, it has a good range of up to 20 kilometers and more, and it doesn't interfere with our GPS frequency range at 1.1 to 1.5 megahertz or the receiver that is at 2.4 gigahertz.
To select appropriate batteries for each vehicle, we focused on two key factors: capacity, shown in the first equation below the table, and discharge rate, shown in the second equation. We needed enough capacity to last the full challenge duration, which is 10 minutes, and a high enough discharge rate to reliably power each system under load. For the UAV, we estimated a required capacity of 9,335 milliamp hours to sustain a 10-minute flight at maximum current draw. Since the drone realistically operates closer to 50% of its max current, we selected a 9,000 milliamp hour battery with a 100C rating, giving us ample headroom for discharge. For the UGV, we used the same method to calculate a required capacity of 7,965 milliamp hours for 10 minutes of operation. Although we didn't expect to have full power draw, we still selected an 8,000 milliamp hour battery, as weight and size were not major constraints for the ground vehicle.
For our base vehicle, we selected the Traxxas 110 Wrestler BL-2 brushless 2WD. The Wrestler For our base vehicle, we selected the Traxxas 110 Wrestler BL-2 brushless 2WD. The Wrestler provided a strong frame capable of holding all our delivery systems and additional components. The BL-2S driverless motor and 2WD drivetrain provided the propulsion necessary to move the UGV reliably. In terms of meeting project requirements, this setup can support a drive load over 20 pounds, which covers our system weight of 13 pounds. It can also reach speeds up to 30 miles per hour, though for our operations we plan to run between 5 and 10 miles per hour for better control. For the delivery system, we built an aluminum frame with 3D printed connectors and PVC rollers supported by brass bushings. The frame is set at 35-degree angle and mounted with long legs directly into the chassis for better drop-off alignment. A 35-kilogram servo controlled by the picksock manages the delivery gate by retracting or extending through a blue 3D printed mount. Additionally, we added an electronic cover which mounts right into the chassis to protect our electronics. Initially, we used the standard Traxxas shocks with a small 3D printed shell added to it. However, these were way too weak. They left little clearance and could not handle this full system's weight. We upgraded these stocks by adding a larger 3D printed shell. This eliminated unwanted compression and maximized the clearance, ensuring that the vehicle could carry the full payload without sagging or scraping the ground.
We will now cover the communication setup we used. Images in this section will be of the UGV, but it should be noted that the same communication setup was also used for the UAV. Additionally, in this section, we will give an overview of our software and scripts that we used.
For the physical setup of our Raspberry Pi and flight controller, we had a JST-GH connector that goes to the telemetry 2 port on our flight controller, and it connected to the DuPont connectors for the Raspberry Pi. And this connection allowed for telemetry data to go between the Pi and the Pixhawk so that our scripts can be sent over and it can create the mission and drive the vehicle around autonomously. For our software that we had to use to do this is MavProxy and MavLink had to be downloaded onto the Raspberry Pi so that the messages sent would be understood by the Pixhawk. We also used the drone kit scripts on the Pi to write our script, which is a script made to go with the Pixhawk 6X. We also used the socket. The socket allows us to create a server on the Pi on the UGV so that whenever the UAV connects to that Pi, it can send the coordinates of the correct Aruco marker directly to the UGV, and then that coordinate can be sent to the Pixhawk. For our UGV script, you can see it here on the right. It starts off by doing preliminary checks, and then it connects to the Pixhawk flight controller. After that, it ensures that the delivery gate is up so the payload won't fall off while driving. And then it'll create the socket server, which will allow peer-to-peer communication between the drone and the ground vehicle over the Wi-Fi router. Then it waits for the drone to fly, find the correct marker, and send the coordinates. And after that, it will navigate to those received coordinates from the server, send those over to the Pixhawk, and then drive to the delivery zone. And it'll open up the gate and deliver the payload. And in green, you can see the timestamps for the starting the ending, and whenever the correct coordinates were received from the UAV. During testing, we noticed that there were some issues with the wireless communication method and how we were sending the coordinates after finding the correct Aruka marker. So let's say the drone was flying and it found the marker at the bottom left of the furthest point away from the car. And then it stays there, centers, and then tries to send the coordinates to the UGV. But if it can't send the coordinates in the script we had, it's where it would return to launch after sending the coordinates. So if it didn't send the coordinates because it couldn't connect to the car due to the long range, it would just sit there until the battery died and fall out the sky. So we came up with a method. We changed it to where it would return to launch first, land next to the car, and then send the coordinates. This way, we didn't have any missing communication or a drone stalling over the correct Aruka marker.
For our ground control software, we elected to use Mission Planner as it provides a wide variety of resources for us. Its main purpose is to allow us to configure, control, and monitor what the UAV and UGV are doing. One of its key notes is it displays live telemetry data, such as altitude, speed, battery status, and any errors or situations that we might run into during live flight or testing. Earlier we mentioned that the HERE4 has real-time kinematic capability, and this allows us, the UAV and UGV, to get more accurate down to the centimeter level by having both the vehicles on the same reference point. Fortunately for us, the elected software Mission Planner has an option of allowing us to input those GPS corrections more easily from an RTK base station that serves as an interceptor. This gives us an overall advantage in our simulations and our flight testing. These pictures give an idea of what it's like to have RTK and not to have RTK, and how accurate it can be from inches away to feet away. Basically, what occurred here was the aerial drone recorded the Aruka marker, and the one with the RTK seems to have the same reference point or same map, so to speak, as the aerial drone. Without RTK, it only gives the ground vehicle an idea of where it was supposed to record or where it was.
We will now get into the results from the testing that we did. One of the tests that we did was a current draw test on both the aerial vehicle and the ground vehicle. On the ground vehicle, this was done by placing an ammeter in between the battery and the motor. But on the aerial vehicle, the motor drew so much current that we couldn't use just a normal ammeter. So for this current test, we used a current probe. Current probe works by measuring the magnetic field that is generated by the current as it flows through the wire. Because magnetic field strength is proportional to current, the current probe is able to take that magnetic field strength and convert it to the amount of current that's in the wire. For the ground vehicle, when throttle was at 25% with no load, 25% throttle being our operational speed, it drew 1.5 amps. And at operational speed with a load, it drew 8 amps. Now, when we were at 100% throttle with no load, it only drew 5 amps, and when the motor stalled, so we held the wheel, the motor wasn't moving, it drew 40 amps. The UAV current draw will be shown on the next slide.
This table shows the thrust results for 3 UAV systems at full throttle. The 6S system achieved the highest thrust-to-weight ratio of 4, offering excellent lifts, speed, and stability. While a thrust-to-weight ratio above 2 is typically needed for safe flight, our mission focuses on scouting. However, due to time, we move forward with the 4S system, which still provides a 1.8 thrust ratio, which is enough for reliable and agile scouting operations.
This is a video of our UGV completing its side of the mission. As you can see in the terminal screen, it's waiting for the UAV to connect and send it the delivery zone location. And in green, there it was. The delivery zone location was sent. Now the UGV is off on its mission. Incorrect landing zone to the left, which it did not navigate to. It's navigating to the correct one to the right. We realized after the fact that the coordinates that we sent were actually slightly to the side, so it actually delivered much closer than it looked like in the video. This is a video of the UAV performing its scouting pattern that we decided, which is the snaking scouting pattern. UAV took off, and now is following the path. You can see in the bottom left the path that was set in yellow, and purple is the path that is following. Once it reaches the end, we had it set to return to home, so it returns to home. This test was performed in 15 to 25 mile per hour winds. In this video, we are testing the autonomous Aryuka marker detection scripts created by the CSC team. Flying the drone manually 10 to 20 feet in the air, it could be seen that the Aryuka marker is correctly ID'd. It was set that this one would be a non-drop zone, so it's printing non-drop zone detected in the terminal. Here is a slide showing our final vehicle designs. In the top left, you can see the UGV final computer design, and then you can see it actually built out in the two pictures beside it. On the top right, you can see the UAV final computer design, and then below that, you can see the two final UAV built out designs. Our original plan for the UAV was to follow a snaking scouting pattern. While this worked well, it was slow, especially when the marker was placed near the outer edge of the boundary. To improve speed, we added a spiral scouting pattern at the beginning. The idea was for the UAV to quickly cover a large portion of the area with the spiral, and if the marker was found during this initial pass, we can complete the mission faster. If not, the UAV would then switch to the more thorough snaking pattern to ensure the marker was located, but just at a slower time. This is a video of us completing Challenge 2 at the competition. To refresh, Challenge 2 was for the UAV to scout the field within the 30 by 30 yard section marked by the cones in this video, to find the correct Aryuka marker, to tell the UGV then to go deliver the payload to that Aryuka marker. So as you saw, our drone took off, and now it's completing its scouting pattern, which is the spiral. And it's searching for the correct Aryuka marker.
Come on. Keep going. Hover.
And here you can see it detects it, and it started doing a centering algorithm.
Good.
And once it's centered, or when it reaches 10 seconds, it'll take its coordinates, send it, log them, and then fly back to the UGV. The day of the competition, we were having connectivity issues with our Wi-Fi, so we implemented it into the code for the UAV to fly back to the ground vehicle before trying to send the coordinates, just to ensure that they were both connected to the internal router that was mounted on the ground vehicle. So here you can see the UAV's landing, and then we'll have about 7 to 8 seconds of delay that we implemented just to make sure everything happened properly.
Good boy.
And then the UGV will start to go.
Good boy. Second part. Give it a second. Yep. You wanna?
Now the
Come on, buddy.
UGV
It does a
received
little
the
bit of a dance
coordinates
before it
and
starts.
is
There you go.
navigating to those coordinates to deliver the payload.
We're zooming with this one.
You can see the delivery zone that came in frame.
Come on, boy. Come on, boy. Come on,
And it
boy!
stops, drops the payload, and does a little reverse to make sure the payload is fully deployed.
Okay. Yeah!
Due to how close the scores were between UTA and UTD, Raytheon decided that they would go ahead and do the bonus challenge, which was to repeat challenge 2, but deliver a heavier payload. So as you can see here, the drone is started doing a scouting pattern, which again is the spiral, followed by the snaking pattern if it does not pick it up in the spiral. The marker was on the very edge, so I'm going to fast forward this so it goes faster.
Is accuracy based?
One of our concerns was how the UAV would handle the wind. As Richard talked about, we were discussing switching systems to a higher thrust system, 6S system, but that ended up not working out. And here you could see one of those concerns come into play. There was a big gust of wind, which took the drone out, hit the cone, but we did not hit the kill switch and the drone recovered. We asked the judges and this was completely fine.
Well, we only have one attempt, dude.
We got it!
And finally, the drone found the correct Ryuka marker and is doing its centering algorithm.
Hey, in racing, that's 2 seconds. To the area.
There's me standing with the kill switch remote, and then there's the drone coming back to land. It should be noted there was no time limit for this challenge. You can see how hard the UAV is fighting against the wind as it's trying to land.
Good boy! Good boy!
The problem that we were aware of, but we didn't fully solve, was our steering servo on the car was the stock steering servo that the car came with. This servo was not designed to operate under heavy weights, but we thought it's fine because once the car is moving, there's a lot less friction and it's easier for it to steer. But as you can see, not only is the car struggling just in terms of torque, it's also struggling to turn. It should have been turning left right now, but it is continuing straight with a slight turn. I'm going to fast forward. Eventually, after the car tried to get as close as possible to the point and realized that it wasn't turning to the point, it gave up and accepted mission complete and delivered the payload. In the script, we had it to where the car would reverse, but for some reason, it did not reverse. Regardless, this counted as our attempt, and since the judges specified that the payload did not have to fully release from the car as long as the system actively tried to deploy it. Ultimately, we were about 6 feet farther away from the payload, or from the correct delivery zone with our payload delivery than UTD was, which ultimately ended up scoring us second place, with UTD getting first place.
For our budget, Raytheon required that the full cost of both of the vehicles competing in the competition be less than $5,000. The ground vehicle, the cost of it came out to $1,825, whereas on the aerial vehicle it came out to $2,052, for a grand total of $3,877, putting us well under that $5,000 mark. For our schedule, we had everything completed before the competition, so we were ready to go. A little bit of more time to test would have been nice, but we had everything completed that we needed to do in order to compete. For some standards that we followed throughout the course of our project, we have IEEE 1937.1 and IEEE 1936.1. We followed IEEE 1937.1 by implementing information logging through the Pixhawk and the Raspberry Pi, power management by using the power module for digital monitoring, and structural stability of the parts that the mechanical engineering team designed. Additionally, we followed IEEE 1936.1 through the use of a ground control station and an onboard computer, which was once again the Raspberry Pi. To conclude, we were able to complete all the qualification tests and the competition challenges in order to score second place out of 10 teams. Some recommendations we would give to future years would be to use a more robust peer-to-peer communication method to avoid connectivity issues, have a better UAV thrust-to-weight ratio by possibly using a hexacopter, try to get a test drone kit or a pre-built drone so that way you can test with it while the real drone is being made. Use a ground vehicle that has more torque in it so that way weight is not an issue. And also add more sensors to the aerial vehicle and the ground vehicle, such as LiDAR or more cameras, so that way the GPS is not the only means of navigation.
Thanks for listening to our presentation. If you have any questions, please leave them in the comment section below. We wanted to take a moment to provide a special thanks to Raytheon for hosting the competition, and a very special thanks to Professor Dr. Wetz for being such a big help and supporting us throughout this project.